All right. Today we're going to look at algebra-based magnetism. So this is going to review everything involving magnetic fields that isn't Ampere's law, Biot-Savart law, or Faraday's law with like flux functions. So we will do some induction, but it's the sort of motional EMF case. So beginning with the purely qualitative stuff, we got magnetic field lines. So where does magnetism come from microscopically? Well, the origin of all of our magnetic fields are moving charges. So if we think about where that smallest level of moving charge is, that's just your electrons. So we say the motion of electrons within atoms, which we sort of visualize as this concept called spin, not super important. Classic analogy just says imagine a spinning ball, except it's not a ball and it doesn't spin. But to be magnetic on the macroscopic scale, we need these sort of domains, which is the name for like the magnetic alignment sort of a material and sort of its chunks. Its sort of chunks need to align. So what that means, for example, if you split up your material into like these different countries, you'd sort of need your domains within each specific region to generally match. So each of these chunks would be called a domain. And mostly these will cancel except for a couple very special elements like iron. So the strongest level of magnetism you can get is known as ferromagnetism. And that's where these magnetic domains remain aligned with a magnetic field. So for example, if you put a magnetic field in the upwards direction, the domains in a ferromagnetic material would all just quickly become aligned with that vertical direction. And even when you take out the field, the domains would remain aligned. Whereas paramagnetism, you don't get as much of an effect, and that effect doesn't persist when you remove the field. So we say like ferromagnetic materials, those are like your sheep of the world, where you tell them how to think, and they'll continue thinking that way until someone else comes by and tells them how to think. Whereas paramagnetism, these are like your orbiters, where they might change their opinion if someone's around, but as soon as that person leaves, they're back to their own beliefs. So the really only experiment we have involving this qualitative stuff is testing if we have ferromagnetism or paramagnetism. Well, ferromagnetic is like that is your like stronger of the two. So you're really just magnetizing something, usually by rubbing a nail against a bar magnet is the classic. And then you remove the bar magnet and see, is your substance still magnetized? So if the field is still there, even when you remove the external one, you got a ferromagnetic substance. But if the magnetism is gone, you got paramagnetic. Now we're going to talk about field lines. So what are magnetic field lines' defining features? Well, there's really one main one, and that is the fundamental principle that magnetic field lines must form closed loops no matter what. No matter what. Even if this goes against what rule you're thinking, you know the magnetic field lines must loop in on themselves. And we say that outside a bar magnet, north poles are sources of magnetic field lines and south poles are sinks. So it is important we say that is what's happening sort of outside the bar magnet. What is magnetic flux? So this is our first use of flux in this course. We say that flux, if you have a 2D surface, which is like a loop, it's the amount of field that pierces an area. So we define flux through a surface as B perpendicular times A, if the field is constant, where this B perpendicular is what part of the field is actually piercing the loop or the surface. In 3D, we interpret flux more as like a flow rate because there's a clearly defined in and out if you have a 3D shape versus a 2D one. And that matters here because we have our first Maxwell equation, which is Gauss's law for magnetic fields, which states that if you have a closed surface, the magnetic flux, the net flux at least, must be zero. So the flux can be non-zero through all the different parts of the surface, but the flux needs to cancel because there can't be any flow into or out of the surface. So this applies only to 3D shapes. So what you can have is you can have a situation like this where you have a bar magnet and you bring it close to a loop. This is not a 3D shape, right? There's not really a volume here. There's an area enclosed, like this is definitely an area, but it's not a volume. So if you look at the flux, sort of through this loop, and you try to draw some magnetic field lines through there, we would definitely get a sort of net result. So you don't necessarily need to have zero net flux through every type of surface. It is only the closed ones. Where if instead I repeat the experiment with a bar magnet that's near like a sphere, let's say, there is a well-defined in and out. So when the field lines are looping in on themselves, they must somehow exit that surface as well. So that's why it's only for closed surfaces that Gauss's law for magnetism is applying to. Because there really isn't like an in and out, so you only get sort of one sign for flux. We just talk about its absolute value. So why is Gauss's law for magnetism true? Well, it's true because of the looping. Magnetic field lines always form closed loops. So that means you can't just have a source or sink of field lines, which would be where flow comes from, right? If you have a flow out, there must be a source in your surface. If there's a flow in, there must be a sink. But you can't get sources and sinks with magnetism because the field lines must always form a closed loop. So they can't just spawn from a source and they can't just get sucked into a sink. They gotta be equally source-like and sink-like. So this example throws people a lot when we talk about this. Is actually like what happens inside the bar magnet. So like let's say I have this sort of sphere. Let's say I have this sphere that partially encloses the bar magnet. According to Gauss's law, we know that the flux must be zero through this surface because it's a closed surface. But that seems sort of contradictory because what we'd think is that, oh yeah, I just have a north pole, so that's going to be a source. So north pole is a source. So we see that the field lines sort of exit this. So we'd say, oh yeah, the flux is non-zero. But what we forget is that the important rule for magnetic field lines is they must form closed loops. So that actually means that inside the bar magnet, we actually get the field points from south to north in order to cancel out that outward flux, right? Because we see that, yes, it does exit the sphere. There would be flow out of the sphere at these points, but also the field lines come back in and flow in there. So that's what the field line looks like for a bar magnet. It actually points from south to north because the most important rule isn't the source and sink nonsense. It's the fact that magnetic field lines must always form closed loops. And why is this true? Well, it's true because of the closed loops is what makes it true that we can't have sources and sinks. And what this means is you can't have magnetic charge. We have yet to find just the North Pole living by itself. So this tells us that all magnets have a north-south pair. Yes, even if you cut the magnet in half, it'll just grow a new pole at that spot, essentially. So this is unique to magnetic fields, which is why Gauss's law looks very different for E fields. All right, we just got some basic right-hand rule stuff to do here. So again, for charges, we say if you have a positive charge, you can stick your thumb in the direction of V and your fingers in the direction of B, and your palm will be the force. Because the magnetic force is defined as magnetic force. Its magnitude, at least, is QVB, we'll say QV perpendicular B. Where V perpendicular is the part of the velocity that is perpendicular to your B field. So just like E fields act on just any old charge, B fields only act on charges moving perpendicular to the field somehow. So it doesn't have to be entirely perpendicular, it just has to not be parallel. All right, so first I stick my thumb to the right. I stick my fingers up. My palm is pointing at me. So that means the force is in the plus Z direction, which is out of the page. All right. Next, we have a negative charge. Negative charges behave oppositely as positive charges do. So you can either remember to flip it or just use your left hand. So if I'm a negative charge, traveling up, and my field is into the screen, so I point my fingers into the screen, notice my palm is slapping to the right. So this would be to the right. Now, if you did that with your right hand, you would say that a positive charge would accelerate to the left. So since this is a negative charge, it must be to the right. And some people like to just only use their right hand and say negative charges get a backhanded slap for their negativity. Now we run into an issue here because we see that V is to the right, but also B is to the right, and there is just no way that I can point my thumb to the right with also getting my fingers to the right. And this should make sense because the formula for magnetic force relies on V being perpendicular to B somewhat. You have to have at least a perpendicular component, but we don't here. So there's actually zero force. So there's zero force if you're parallel or anti-parallel, right? I also can't get my fingers to point left. Like that also wouldn't work. It has to be at least somewhat perpendicular. And we can get an angle too. So if I do this last case where I stick my thumb up into the right and my fingers into the page, my palm is slapping up and to the left. And since we know that the force is at a 90-degree angle, we actually know that it's specifically, this is going to be our force vector. Because again, the reason we have to use the right-hand rule is there's always two choices for perpendicular if you're given two input vectors. And the right-hand rule tells us which one to take. Because I could have just as easily drawn a perpendicular vector like that is also perpendicular to V and B. So this would be up and left. It's kind of a nice one. So that's all the right-hand rule you could possibly need. This is one of my favorites. We got the velocity selector. So a positively charged sphere, I didn't actually need to tell you it was positive for this part, moves at a constant rightward velocity. So it's really important in these velocity selectors that we're given this fact that it is at a constant rightward velocity. Because if you're at constant velocity, that means that you have no net force because of Newton's first law. So what that means is when you have these crossed fields, you know there's going to be equal and opposite forces caused by each field that are exerted on the sphere. So first we want to draw the E field. Well, E field, that's really easy, right? E field, source and sink, positive to negative. So my E field is just down because of the source and sink rule. Now we want to draw and label the electric and magnetic forces exerted on the positively charged sphere. So here's actually why I gave you the sign, so we could all agree on the free body. We'll see this actually doesn't affect the speed, but it will affect the directions of everything. So first of all, we know that positives like to accelerate with the field, or you could see, oh look, the minuses are down here. So the electric field is definitely trying to pull that sphere down. And then this isn't balanced, so we know that whatever the magnetic force is doing, it must exactly cancel that contribution. So we know the magnetic force must be the same value except upwards. So we know by Newton's first law these forces must balance. But that's not the field, so be very careful because we just said there's this whole process for finding force from field given magnetism, so we have to sort of reverse engineer our right-hand rule to get the B field. So what we know is that the magnetic force is up and we're moving to the right. So moving to the right means my thumb points right, and then the force being up says my palm points up. So again, I'm going to the right, but my palm points up because I'm getting slapped upwards by the magnetic force. And we see that the only way to make that work is for my fingers to point at you. So that means that the B field is into the screen. And you know you've probably done it right because in these velocity selectors, you get all three dimensions out of V, E, and B. So you make like one of these should be in the X direction plus or minus, one of these should be in the Y direction plus or minus, and one of these should be in the Z direction plus or minus. So you should be able to make your X, Y, and Z from that. So what is the V? So this is called the velocity selector because only one velocity can make it through because the B field exerts a force that's dependent on this speed. So all we do is Newton's first law, which says that if our velocity is constant, we must not have any net force. So my electric force QE is exactly balanced by the QVB magnetic force. So we see that E is equal to VB, or V is equal to E over B. This is a pretty common result. I would not say to memorize this because it's 2 lines, but be familiar that this is a thing that exists, this process of solving for the selected velocity. Now here's an interesting little addition at the end. Suppose gravitational forces are not negligible. Indicate whether the value of v required to move at constant velocity increases, decreases, or stays the same. So what would it mean if we can't ignore gravity? Well, if we can't ignore gravity, we're going to increase the speed required because now there is an additional downward force added on my sphere. So originally, we just had an electric force QE down. But now, if there's mass involved, well, there's a gravitational force mg downwards. So what that means is that your magnetic force, QVB, has another thing to balance. So before it was just QVB equals QE, but now it's QVB equals QE plus some other stuff, mg. So your value of V must go up because you need to create a stronger magnetic force because you're not just balancing QE, you're balancing mg as well. So now that we've just talked about the basics of like this sort of balanced B field, E field behavior, and just the force direction, we can now talk about some dynamics with charged particles. So due to this fact that you're always making a perpendicular relationship with this, with V, B, and the force, that means that you're always pushed perpendicular to your path, which means you're not going to speed up, you're not going to slow down, you're only going to be turned. Because those are the three things a force can do, right? A force can speed you up if it's with your motion, a force can slow you down if it's against your motion, or a force can turn you if it's perpendicular. And what do you get if you're constantly turning? Well, that's going to be a circle. So what this means now is that if you're just allowed to let the magnetic field do its thing, that means that the magnetic force is supplying a net force that is called a centripetal force. So again, centripetal is not a noun. This is not like a type of force. This is an adjective that can be applied anytime you're in a circle. So we usually use this relationship that the QVB magnetic force is supplying a net force with magnitude mv squared over r. So this is the centripetal force relationship. So this is our sort of representative example where we're sending a charged sphere into a B field. It says we exit the field with leftward velocity, and we're going to be interested in drawing the path. We want the radius of the path and the time spent in the B field. So QV cross B, I have to point at me, right? These field lines mean they're coming at me because I'm seeing the arrow tip. So it's getting pushed down. So that means it's going to have a circle whose center, it's going to, if we say the particle sort of enters right here, circle center is going to be somewhere below me. So I'm just going to draw a circular arc. Now, I think it's easier probably to just do something like that. Can we make it a bigger arc? Probably not. There we go. That's about as much as I can do. So what this is going to essentially be is a half circle, right? Because it says we exit with leftward velocity. So that is the key to this problem being like totally solvable to the point where we know it's going to exit with that same velocity, just sort of turned around. So we know we have made exactly a half revolution. So we're going to derive an expression for this radius using that relationship from earlier that we know that the magnetic force is supplying a centripetal force. So QVB is equal to mv squared over r. One of the v's cancel, so we get QB is equal to mv over r. So QBR is equal to mv. So mv is equal to QB. Sorry. So R is equal to mv over QB. Yes, I know it technically should be lowercase, so let's do that now. I don't know why I made it lowercase q this time. And there's some cool qualitative stuff to do with this, where you can see like, oh yeah, it makes sense that it's a bigger radius with bigger mass because it's harder to turn. It makes sense that it's a lower radius for lower q and b because that means the turning force is greater. There's a lot of cool stuff to do with this. Taking my practice exam, you've seen that QQT. What about the total time spent in the magnetic field? This is kind of an interesting one. So what we do know is it's not constant velocity, because velocity is direction and it's getting turned. But since you're getting turned, that means that we have constant speed. So if you have constant speed, you can just use some middle school physics. And I say this is middle school physics because it's the most basic equation you have, where like the distance traveled is equal to your speed times the time spent. So we're interested in time. The speed v was given to us. So all we need is that distance traveled and we can solve it. So what is that distance traveled? Well, we know that the distance is equal to, well, how far does the sphere go? Well, the sphere travels this distance, which is exactly the diameter of a circle. So it goes 2 radii worth is sort of this area. So its displacement was 2 radii. So how much is that? Well, it's a half circle, so it's just a half circumference. So d is 1/2 of a circumference. Maybe that's spelled correctly. Who knows? Circumference is 2 pi r. But we also figured out what that was. We said that r was mv over qb. So this is kind of just living off the side here. So now we can just solve, where we said our distance traveled is half of a circle. So it's not 2 pi r, it's just pi r. So we see, interestingly enough, a v actually gets canceled out of this expression. So we get the time spent in the field is going to be m, it's going to be pi times m divided by qb. That's kind of interesting. Interesting result for sure. That's about as much as you could be asked with circular motion. Sometimes we like to combine this mass spectrometer piece with a velocity selector, so you might have to plug in this relationship in for v if you went through a velocity selector first. So be aware that that could exist. All right, that's what B fields do. Now we're going to look at where B fields come from. So we have the B field generated by a wire. So what is the shape of the B field generated from a wire? Well, magnetic field lines form closed loops around a wire. So these are circles. And the direction of circulation is the right-hand rule. So we'll see. This is gonna end poorly. Anytime we got some 3D drawing perspective, you know it's a bad day for me. So if we carry a current, if we're carrying a current I towards the top of the page, our right-hand rule for magnetic fields says that it forms a circle. It forms a circle, and your fingers circulate if you point your thumb in the direction of current flow. So if I point my thumb up and to the right, I can see that the magnetic field is going to, we know it's going to be a circle. So it's going to sort of pop out of the page. Just clearing my picture here. Okay, that's actually not terrible. The magnetic field is just sort of wrapping around the wire, and it's going to go this way. And it's going to disappear into the screen at some point, but this is essentially what's going on with it. All right, that's not the worst thing I could have drawn in the world. It's pretty bad, but I've drawn worse. I think we get the idea. What's the formula for calculating the B field from a long wire? We will derive this with ampere. This is absolutely something to commit to memory. B wire equals mu naught I divided by 2 pi r. Just memorize this. You can easily derive it from Ampere's law, and there's a lot of intuition here because all this says is that B from a wire is caused by current, and it's distributed along a circle. That's where the formula comes from. It's a current over a circle. Currents generate the wire. The field circulates around a circle of radius r, and the mu naught is there for proportionality. All right, let's get some net B fields here. So we have a couple of different scenarios. So first, we want the net field at the midpoint of the line connecting the wires. I should say the separation we're going to say the separation is equal to D. I needed to put that in here. The separation of the wires is D. So what that means is that point P is going to be a distance D over 2 from each of these wires. So we can go ahead and just kind of look at what the field direction is doing. So if I stick my fingers or my thumb sort of pointing up, I see that the B field from the left wire pops out of the page on this side, and it pops into the page on this side. And if I do the 4i, we get the opposite field orientation because it's going to pop out of the page and then into the page. But also these fields are not created equal, right? Because the 4i has more current. So actually, just to illustrate this, I might draw a big circle here and a big X here. So that's going to tell me my net field at point P, even though the circle and the X are going to cancel, they don't fully cancel, the circle dominates. So I actually know that my net B field is going to be out of the page. And we actually do want to derive an expression. So anytime you want the net, you should do some sort of vector addition, show us that we understand superposition is happening. So B is mu naught I over 2 pi r. So for the first wire, mu naught I, because it has current 1i, and the distance from the wire is D over 2. And that would be a field in. And then we have mu naught 4i is the current in the other wire. And that distance is also D over 2, but that field is out. That's how I like to manage my vectors. Last year I was more of a k-hat person. I change whether I like sometimes I might say this is a k-hat unit vector, and this is a negative k-hat unit vector. No, that's not true. Other way around. I might say that this is like a negative k-hat and this is a plus k-hat and do it that way. It's up to you. I like in and out because I think it helps us see subtraction better. So let's see. Divide, that eliminates the pi. That eliminates like the 2 down here. And then same idea. So we essentially have 1 copy of this in, and we have 4 copies of it out. So our net result would be 3 mu naught I over pi d, and it's out of the page. And again, you should have kind of been like able to figure that out. Like if you know if the B field from one of these wires is B, from this wire is B, you know that this B field would be 4B, but in the opposite way, so you get some sort of a 3 happening. So pretty straightforward there. So if your wire is in the XY plane, your B field is going to be perpendicular. Now we have the other case where our currents are in the Z direction, so our field will be in the XY plane. So remember that we circulate, where if I stick my thumb in the direction of currents, my fingers are going to wrap around. So for my single I, that's a current that is into the screen. So my fingers like to wrap clockwise. So for this wire, the field looks like this. I know we don't need it at all these points, but it just illustrates what's happening. Then for the 2i, it's going to be counterclockwise, counterclockwise. It points at me, so my field circulates like that. And actually, just to show sort of what's going on here, that the 2i is sort of winning, I might give it 2 arrows, just to show it's going to dominate over the 1i. Not that there's going to be like a total cancellation or anything. So that means the net field at P, since this is a square of side length S, it would have 2 ups and 1 left. So I just draw a field that's like that's more up than left. And we want to find the magnitude of this. So we know that B from the 1i is just going to be mu naught I over 2 pi s, and that field is directed to the left, whereas the B field from the 4i is going to be 4 mu naught I. Sorry, 2. Sorry, I thought the last one. B from the 2i is going to be 2 mu naught I over 2 pi s, and that is directed up. And I'm not going to simplify on purpose, just so I can like show this common factor. So these are not just addition or subtraction, right? Because they're at vectors to each other. Left does not add or subtract with up. They create a triangle. So if I put this field contribution into a triangle, we get a leftward field equal to 1 copy of mu naught I over 2 pi s. And then for our other field from the 2i, we have 2 copies of mu naught I over 2 pi s. So now you can probably see why I wrote it this way, because now it's a lot easier to sort of add these vectorially and see what the number in front has to be. Because we know our answer is going to be some number now times mu naught I over 2 pi s. So this is our net B field. So let's do that. So of course, this is just the Pythagorean theorem. So the magnitude of our net B field is just going to be, the number in front is just going to be 2 squared plus 1 squared under a square root. And everybody had mu naught I over 2 pi s in common. And 2 squared is 4, 1 squared is 1, 4 plus 1 is 5. So I get root 5 in front times mu naught I over 2 pi s. So I never plug in letters into the square root when using Pythagorean theorem, because you always know that the units have to be the same if you're adding things in a triangle. So I'm never going to put that in the triangle because I know my answer is going to just be some number of these, some number of mu naught I over 2 pi s's. So that just helps me personally not make any like silly algebra mistakes, because if you plug this into the root, it's going to factor out because both of these terms would have that squared quantity in them. All right, lastly, for our B field from wires, we have, suppose you want to find mu naught using a current carrying wire, a magnetic field sensor, ammeter, and ruler. So what can we measure? Well, current carrying wire, since we have an ammeter, we can get the current. We can also measure the magnetic field B. And we also have a ruler, so we can get the distance R. I didn't actually tell you what you're allowed to change here, so there's a couple ways to do it. The intention is that you take the field sensor and probe at different distances from the wire. So we'll do that one first. So like you could collect B versus R and just measure the current through the wire once. You could also measure B versus I and do that as well. I'll show both. So first, we know our equation is B equals mu naught I over 2 pi r. So if you do not change the current in the wire and instead change the distance, you could write B is equal to mu naught I over 2 pi times the quantity 1 over r. So the intention here is you could graph B on your y-axis, you could graph 1 over r on your x-axis, and the slope is mu naught I over 2 pi. Or you could have said, I'm just measuring the distance once, and I'm not changing the distance, but instead I'm pumping more and more current into the wire. That's also totally legal. I could have said B equals mu naught I over 2 pi r, which is the same thing as mu naught over 2 pi r times I. So I could have just as easily said B goes on the y-axis, I goes on the x-axis, mu naught over 2 pi r is the slope if I just measure the distance once and change the current. So there's a couple approaches here. And also, this isn't exhaustive because some people in the audience really enjoy just putting as much garbage in the slope as possible, or sorry, in the x-axis box as possible to make mu naught your slope. So I could have graphed B versus I over 2 pi r to get a graph whose slope is mu naught, or I could have graphed B versus I over 2 pi r to get a graph whose slope is mu naught. Both of those things work out. Now I notice that's the same. Yeah, interesting. All right, now that we talked about these currents, we're going to talk about their forces exerted, because we know that QVB, we get forces on moving charges. Currents are moving charges, so of course currents will feel a force that's exerted on them by a magnetic field. So what's the general form for the magnetic force on a current carrying conductor? Well, QVB sort of gets upgraded to Bill. So I call this the Bill force. its direction is still determined just by QVB. But be careful here that just like the B field only acts on charges moving with a perpendicular velocity component, you need part of your current traveling direction to be perpendicular as well. So be wary of that. And now what we use more often than just BIL by itself is looking at wires interacting with each other, because we know that two wires are going to put B fields at the location of the other wire. And since those wires will be carrying current in a B field, they're going to experience a Bill force due to each other. So we could say that we have like these two wires. They carry currents I1 and I2. We'll say they're separated by a distance d, and we'll get their force. So we can actually find the direction of the force on the wires first. So if I do my wrapping around, we'd see that the I1 wire is generating an into the page B field. So if I do QV cross B with that B field, wire 2 is actually getting slapped towards wire 1. So we know the force is going to actually be attractive. And I know that they're actually going to be pointing at each other because of Newton 3, right? Equal and opposite reaction. So there's that. So now we can get the expression, because we know that the magnetic force is going to be B. Let's find the force on 1, just so we can be clear. We'll say that F on 1 is equal to the B field generated by 2 times I1 times L. And again, we have to do the opposite field, right? Because you can't exert a force on yourself. So we know that the force on wire 1 is due to the field from wire 2. So B2's field is just mu naught I over 2 pi r. Let's use r just to be consistent with previous terminology. I1 L. So we get sort of this fake Coulomb's law where we get mu naught divided by 2 pi as a prefactor. And then we'd get I1, I2 times L divided by r. So we sort of get this Coulomb's law idea. So the force between two wires is proportional to the current product, the length, and then divided by the distance between them. So the attraction-repulsion rules are actually opposite of the charge rules. My class knows what name we have given this theorem that I won't say right now, but we know that like wires attract one another. So now we'll find the net force per unit length on this rightmost wire. So this is an important thing to also know, that since we said that F from wires is equal to mu naught I1, I2 over 2 pi r times L, if we have long wires, if they're really long, infinitely long, they'd have infinite force. So instead, we're just looking at the force per unit length, which is just that expression with the length taken out. So this tells you like how much force is exerted on each meter of wire, which is sometimes better to look at. So now it's looking much more Coulomb-like. All right, let's do it. So rightmost wire. So the rightmost wire is getting repelled by the 2i, because opposite currents repel, and it's being attracted by the 1i. And now the 1i current is lower, so we actually know that the attraction is going to lose to the repulsion. So we can just set this up like a little Coulomb's law type problem, right, where we have our net force per unit length. I am using lowercase here. I like to use lowercase for like force per unit length. It's just going to be vector addition, right? I have F from the 2i plus F from the 1i. And now our two expressions. We have mu naught times the product of the currents, so the 4i and the 2i, divided by 2 pi d. And that's going to point right. And then we have mu naught times 4i interacting with the 1i, and that distance isn't d, but it's d plus another d, so 2 pi times 2d, and that's going to be left. So we'll see what this is equal to. Well, let's see. We're going to get a pi d on the denominator in both of these cases. this is going to turn into 4 mu naught I squared over pi d. And this is going to turn into 1 mu naught I squared over pi d. So we essentially have 4 to the right minus 1 because we have that pointing to the left. So we get 3 mu naught I squared over pi d right. So a little bit of arithmetic there, but pretty straightforward example. We just do our net forces. And again, you could have also reasoned that, right? Because not only does the far wire have half the current, it also has double the distance. So it had half the current and double the distance, so that force is going to be quartered, right? That's why we get a 4 and a 1, because it had half the current and double the distance. So that makes sense. All right, now we'll do some more complicated force scenarios. So we have a conducting loop, side length S, there's a B field down. We want the Bill forces on all the sides of this. So I'm just gonna go clockwise. I always have to think about that. I would never say it wrong. I could draw it right. I just get the words. You know how it is. All right, top QV. Right, current is the direction of positive charge flow, so that's why we're using our right hand still. QV cross B. My palm is slapping into the page, so this force is Bill or B's because it's a square of side length S. My hand doesn't work that way, right? We're going parallel with the B field. I can't manipulate that. So we got 0 force here. And by symmetry, we get 0 force here. And also by symmetry, if the current is just flipping direction from the top to the bottom, this isn't an into the page force. This must be an out of the page force, BIS. So again, we could check that, right? QV cross B. My palm now slaps at me, so that is out of the page. So we see that going around the loop, we have the top side, the right side, the bottom side, and the left. Well, so top we said was BIS. Right we said was 0 because of parallel. Left we also said was 0 because of parallel. And then the bottom we said was BIS once again, except it was out of the page. So now we can describe the net translational and rotational motion. So first, notice that all the forces cancel. So since net force is 0, because BIS out, BIS in, plus 0, everybody cancels. But that's actually not going to make the rotations cancel. So it is true that the net force cancels. So the net force will cancel. The loop will not translate. But if we think about what this is going to actually do, we're pushing in here and we're pulling out here. So the top of the loop is trying to swing into the page and the bottom of the loop is trying to swing out of the page. So we're essentially going to get rotation sort of about this axis. So we actually are going to get a net torque. Now, you will not be assessed on this in AP Physics C. I doubt you'd even see a net torque question like this, but realize that if you are in a uniform magnetic field, right? These square loops or these rectangular loops will not translate, but they could rotate if you have a situation like this. So the net torque is not 0 because the rotations are helping each other. And again, I encourage you to try to visualize this in 3D. Like pick up your phone or some device and try to push it like this. You'll see it starts to spin. So that's that. And now instead we have a more complicated example where we're showing that the force need not be 0 if there is a non-uniform field. So for the last sort of time here, we see that if we have a wire a wire is going to generate a B field, so I wrap my fingers. So it's going to be out of the page up here on this side, and it's into the page on the other side. So why will we get a net force in this case? Well, it's the same scenario. It's the same scenario of our like clockwise current. But now the B field is not constant. So we're going to get sort of a large B field on the left end of the loop, medium B field, and small B field. So we see that we are going to get a bigger force on this left side. It's going to get pulled more. And we actually can compare all the forces already without doing any math, using like the attraction rules. But we'll think about that as sort of an aside here. So if I do QV cross B, we see that sort of as expected, my left side is going to get pulled, we'll say with a lot of force because it's close. Towards the wire, right? Because light currents attract. So it makes sense that we got a leftward force here. Then, by symmetry, we know that there will be another force the other way on the right end of the loop. And since the B field is weaker at that end, we know that the right force is going to be less. And then on the top and bottom, if we QV cross B that, we see on the top it's actually going to point up, and on the bottom it's going to point down. So this loop is sort of trying to expand. So those forces would sort of be like intermediate. So we do see that, yes, these two are going to end up canceling because there's perfect symmetry there. But due to the fact that this entire side of the loop is closer than this side to the wire, we do get a net force. We do get a winner there. So let's find the magnitude and direction of the net force on the loop. So we know that the net force is going to be the force on the left side of the loop plus the force on the right side of the loop. So the force on the left side of the loop, we can just get with Bill or the wires formula. I think I'm just going to use the wires formula, honestly. I think the wires formula makes more sense here. If you would like to start from Bill, you could totally do that and just plug in, but we're really just going to end up in a roundabout way, sort of re-deriving this formula. So on the left side of the loop, we know we're always going to get we got mu naught. Both of our currents in this scenario are I, so we're going to get a mu naught I squared. The length of the loop is S on that side times 2 pi, and the distance between the loop and this side, between the loop and the wire for this left side is just 2S. And we said that force is going to be left. Then we can do the same thing over here. The currents are still both I, the side length is still S, but then for the distance, it's not 2S, it's 2S plus the square's length S. So it's 2S, it's 2S plus 1S, which is going to be 3 S's worth. And that is to the right. So now we'll do our good old subtraction. So let's see, this is going to end up being 1/4 mu naught I squared over pi. Yeah, because the S's actually end up canceling here. So that's going to be left, and then plus no canceling here. And then we can work that out. So it's really 1/4 minus a sixth. So 1/4, that's 3/12. 1/6 is 2/12. So 3 minus 2 is 1. So we actually just get 1/12 mu naught I squared over pi. And that net force is directed left. So this is a hard one for sure. This is in the harder category. What's the magnitude and direction of the net magnetic force on the wire by the loop? Well, that seems quite involved, having to find what all these different currents are doing, but it's actually not, right? We just found the net force on the loop by the wire. So this is just Newton's third law. For a reaction, there's an equal and opposite reaction. So by Newton, Oh, fancy. I wrote out the word third today. By Newton's third law, it's just going to be 1/12 mu naught I squared over pi right. So that should also make sense that if the loop is attracting, if the wire is attracting the loop is attracting the wire. So it actually makes sense that we are going to get the net force attracted that way. And if you do the computation, you see it is really just the same computation we did here, right? Because each of these wires are exerting canceling forces once again. It's just the directions would be flipped from both, so we get the right. All right, last section for magnetism is all about motional EMF and the Hall effect. So what is the Hall effect? Well, the Hall effect is this fact that if you're moving a conductor in a B field, the charges will separate. So what that means is that moving a conductor in a B field generates this potential difference because positives will get pushed towards one end of the bar, negatives gets pushed towards the others. So we can derive an expression for this Hall effect voltage. So what's going to end up happening is I think we'll actually just use this as an example to derive it, where if you move in a B field, positive charges will get slapped one way. So in this case, in this bar, positive charges are being slapped towards the bottom end of this bar, which means the bottom of the bar is more positive than the top. So we have this sort of E field that will be induced in the bar. Again, we just QV cross B it to see that. QV cross B. And then we can derive an expression for the Hall effect voltage. So I really should have put this question beforehand. So what is happening here? Well, what's happening is that when everything is nice and balanced, we get an E field inside of this bar that is working to exactly cancel any forces generated by the magnetic field. So what we know is that just like the velocity selector, the QVB magnetic force is exactly balanced by the QE electric force. So we get the electric field inside the bar is equal to V times B. Now, we don't want this. We want what's called the Hall effect voltage. This is the Hall effect electric field. So we want the Hall effect voltage. And remember, our potential relationship says that delta V equals E times D if we have a uniform E field. So all we have to do to get delta V is just multiply both sides of this field expression by the D that the field acts over, which is that length of the bar. So we can just say E times L is equal to VB times L. So we just multiplied this on both sides, totally legal. So ED is delta V. So we get delta V from the Hall effect is just VBL. This is also on the memorized list. This is also on the memorized list. It is very straightforward to do this, but VBL comes up way too often to not have it memorized. Figure out whether it's positive or negative potential difference. Just draw your charges. And how does this relate to currents? Well, if you give this bar sort of a circuit to be a part of, you can get a current flow. So if you put your Hall effect voltage across a circuit element, so if I like connect a light bulb here or something like that, we get a current. So that's how it connects to that. All right, now we are moving a conducting bar across a set of U-shaped rails. So this is like the Hall effect motional EMF question. It's the bar on rails system. So first we're going to draw the charges and the E field within the bar. Oh, we already did that. So it is important with these rail systems to actually know that like the E field and the current and all that actually all stops at the width of the rails. So just be wary of that fact. And we know that electric field points from sources to sinks. So there's your E field. And now it wants us to draw this sort of effective circuit. So here we're going to have a current flow because we're connecting the ends of the bar to each other. And we're saying this conducting bar has a resistance, so it will have some sort of current. So effectively, we are creating a circuit where this bar is no longer a bar. This bar is now a battery, with its bottom end being at higher potential. So we have essentially created this circuit. And there's an effective resistance R within the circuit itself. We'll see if this attempt is better. Yep, I would say it is. So the induced current can always be found by the Hall effect. You just know that current sort of originates from your positive end of the battery. So we get a, gotta think about it again, we get a clockwise current. This is not the only way to know that the current is clockwise. If you know things about Faraday's law and Lenz's law and flux changes, you can see, oh, I'm going to the right. I have more and more circles. So I got to generate a current that fights the circles. So no, I don't want circles, circles, circles. I want x's, 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 and that's created by clockwise. So you could have also determined it's clockwise using Lenz. All right, what's the EMF induced in the bar? Well, this is just the definition. EMF is the Hall effect voltage. VBL, current induced in the bar. Well, we have EMF, so it's just Ohm's law. VBL over R. What's the magnetic force acting on the bar? Include direction. Okay, so we'll come back to the direction thing. But we do know that this is a current carrying wire, or at least a current carrying conductor, so it's subject to the Bill force. B is B. We just solved for I. I was VBL over R. So we get this interesting squared expression that if you've been following the class closely, we're kind of familiar to seeing this. And I always like to put the V outside just to show that this is a like drag type force because it's dependent on velocity. So this is just a fact that you could also put in your brain, that the magnetic force is always a resistive force in these bar problems. And that's due to this idea of Lenz's law, where the flux change is always being opposed by the current. But again, if you do your QV cross B, we're saying the current in the bar is actually going to flow sort of down. So the current in the bar flows down, and I think this is worth a diagram, where if we redraw sort of our rails system with the bar, our current is flowing clockwise, so this is our current. Our B field is out of the page. So if I do QV cross B, notice my palm is slapping to the left. So that actually does mean my force is to the left. Now it is just a fact that the B field is always going to resist your motion. That is a fact of our universe. All right, what is our rate of energy dissipation within the bar? Well, pick your favorite power formula. We got I delta V, we got I squared R, we got V squared over R. Usually we'll know about EMF, so usually it's this one. So we're going to say this is equal to the induced EMF divided by the resistance, and we said that the induced EMF is just our good old Hall effect voltage, VBL. So what's the rate at which energy goes in? Because again, if we're pulling this to the left at constant velocity, there must be something fighting this magnetic drag. So what we have, we know that we have this sort of magnetic force fighting our motion of the bar. So we must actually be exactly countering that with some sort of like external pulling force. So we can say that the power from the external force, as defined in mechanics, is force times velocity. And force is going to just be equal to the Bill force, which we said was B squared L squared over M times V from FV. And oh, look at that. We get exactly, oh, where's this M? Where's this M spawning from? No, this is R. Sorry. VBL squared over R. Huh, look at that. That is exactly the same as the rate at which energy is being dissipated. So this is a cool little energy conservation trick, is we can always figure out the power input by looking at the power output, because the energy of the system must be conserved. So you could have just said, oh, it's got to be equal to the power dissipation rate. So we'll use these terms interchangeably for that reason. All right, last one. A conducting bar of mass M is on top of a rail system. We release the bar from rest, and we slide the bar down the rails. This is basically the same problem, except it's vertical, and we are not helping it. We just drop the bar. Draw the induced charges, and draw the current flow in the circuit created. Okay, well, I'm going to be falling down. So I'm going to be falling. So my So my V is down for the bar, and my field is out. So I slap my positive charges to the left. So that would mean this end of the bar is positive, this end of the bar is negative. So I've essentially created this circuit. So this is my positive end of the battery. So my current will once again be clockwise. And this is that same flux reason as before, actually. You'll see you're still getting more and more circles, so you got to fight it by getting more x's, so that is clockwise. All right, let's say the bar is moving along the rails. Draw a free body diagram for the bar. So if the bar is falling, well, of course the bar is falling, so we know it's going to have some gravitational force, mg. But also, we know from last time that there will always be this sort of magnetic drag. So it's not just going to accelerate unopposed, because as I induce current in the bar, which would actually be going to the left, you could check that if you QV cross B your bar would be slapped up by the magnetic force. So we do get this Bill force that resists the motion. So is the acceleration of the bar going to increase, decrease, or stay the same? Well, think about this as like different snapshots in time. So maybe we're just going to, maybe I'll take this out for a second. There we go. I just can't get this to do what I want. Trying to be a copy paste cheater here. All right, so at a short time, before the bar starts moving, it's getting pulled down by gravity, and that's all. That's all you got there. Then we'll look a short time later, and then we'll look a long time later. So a short time later, the bar is going to be moving, so it has a little bit of speed, and the Bill force is going to fight you a little bit. Then a long time later, you're going to be moving really fast, and so fast that the Bill force actually exactly balances your weight, so you stop speeding up. So what's going to happen is the bar is going to accelerate at a very fast rate. It's going to accelerate downwards at g. Then the Bill force is going to fight that acceleration, so it accelerates less and less and less. Your velocity is still going to increase until eventually the Bill force balances out. So here's that argument. Magnitude of the bar's magnitude. Oh, lovely. Magnitude of the bar's acceleration decreases over time. As the bar accelerates, its speed increases. So this increases the induced current, so the Bill force increases. And if your resistive force is increasing, you're getting less and less net force, so you're getting less and less acceleration. Let's prove that mathematically. So if we want acceleration, we know acceleration is F net divided by m. And we can say that F net is equal to the forces helping the motion of the bar minus the forces hurting the motion of the bar. So what's helping the bar move downwards? That's the gravitational force mg. What's hurting the bar's motion? That's the Bill force, the magnetic force BIL. And just like before, the current in the bar can be found just by taking the Hall effect voltage divided by its resistance times L. So this is going to tell us that the net force is equal to mg minus b squared L squared over r times v. So that means our acceleration of the bar would be all of that divided by the mass of the bar. So I take out a mass from the first term, and I also put a mass on the denominator of the second term. All right. Determine the speed of the bar after a long time. There's two methods of doing this. One is after a long time. We would see that after a long time, the acceleration is equal to 0 because I have stopped accelerating. My speed is constant. So I just set my acceleration expression equal to 0. I'm going to call this VT for like terminal speed. So V terminal would be mgr divided by b squared L squared. Another way of doing it is instead of looking at acceleration, you just want to look at the forces. So after a long time, the force is balanced. So you'd say the gravitational force equals the magnetic force. So mg is equal to Bill. But we said earlier that current was VBL over R. So we get the same idea because we get mg is equal to b squared L squared over R times V. So we'd send the R to the top, b squared and L squared to the bottom. So once again, we agree that the terminal speed would be mgr over b squared L squared. And it does make sense that if you have a more massive bar, you have more weight to balance, so the speed has to be higher to generate the same magnetic resistive force. Makes sense that if you have more resistance, you have less current, so you got to go faster. Same idea. These are both magnetic force related items, so it makes sense that those are hurting your V terminal. So what does the speed of the bar look like? Well, we know that initially your bar is not moving. And a long time later, it's going to have some sort of terminal speed. So we actually know that this is a curve that is going to have a horizontal asymptote. And we actually know what that is. It's mgr over b squared L squared. So what that does for us is that means we're just going to have some sort of vertical or horizontal asymptote curve like this. We get an exponential approach, or an exponential zombie, if you will, to use the terminology. So you could actually, using calculus, you could come up with a function for this, and you'd see that V is equal to mgr over b squared L squared times 1 minus e to the negative b squared L squared over mr times t, I believe is what you'd get, because we know that at infinity, that's the speed, and at zero, it's zero. I do believe that this is the function that models it. Just by looking, I think I didn't mess anything up. Alrighty, yeah, that's algebra-based magnetism. A little bit longer than I thought it would take, but a lot of good problems in here.